Hi guys, welcome to this set of videos. These videos are going to follow along with the notes that come out of your textbook from Chapter 9, Section 4. Now what we've been doing here in Chapter 9 is we've been taking a look at conic sections. And the way that works is we just simply take a conic and we divide it using a plane into a certain section, and the profile or the projection of that section is going to form one of four shapes. We've already looked at parabolas and circles, and now we're going to go ahead and take a look here in Section 4 at ellipses. Now what you've seen so far through these sections is that essentially the algebra is you being able to complete the square. And then really all you need to be able to do is use the formula sheet that I've given you once you know the value of A, H, and K to really just sort of plug and chug, all right? You find the formula for what I've asked you for, plug in the value of A, H, and K as appropriate, and get the answer that I have asked you to find. We're going to do the exact same thing here for ellipses, but a couple of objectives or learning targets to sort of help us focus as we go through these notes. You'll need to be able to write the equation of an ellipse. That's just like what we've seen before for circles and parabolas. And you'll need to be able to graph ellipses just like before what we've seen for circles and parabolas. Let me go ahead and slide on up here. Again, we're working on conic sections, and now we have come to number 3, ellipses. Now remember, the way that you find the ellipse is you take that conic, which is two cones, put point to point, and what you'll do is divide that conic with the plane, which they show you right here, at kind of an angle, right? If that plane were perfectly horizontal, you would get a circle. But if you slightly tilt that plane at some angle, it could be really steep, could be really shallow, right? But what you get is the shape of an ellipse. This profile right there is the shape of an ellipse, which if you were to project that onto a coordinate plane would be an elongated circle. So we're on to ellipses here. Let's go ahead and take a look at the two forms that these can come in. Again, just like with circles, right? We see this idea of there not being an H and K and there being an H and K. The only difference here is this. This one is centered at the origin, which simply means that H and K are 0, 0. Again, if you were to plug a 0 in for H, it would go away, you'd be left with an X squared. You plug a 0 in for K, it would go away, you'd be left with a Y squared. We'll talk about what the A squared and the B squared mean in just a second. We'll get to that. The vertex form then, because the H and the K are still there, this is going to be an ellipse that is centered at HK. Now, one other thing that we want to look at here when it comes to ellipses, because it is slightly different than a circle. Remember, with a circle, you can't really have a vertical or a horizontal, what's the word I'm looking for? A vertical or a horizontal alignment, or a vertical or a horizontal, what is the orientation? Vertical or horizontal orientation, because a circle is the same all the way around. But with an ellipse, we will have a circle that's sort of elongated, meaning that we're going to have an axis that's longer than another. We'll have a major and a minor axis. And so what we're going to look at here on the next page is a picture of ellipses with all of, sort of the diagram with all the terms and things you'll need to know about ellipses. But what you'll see is we can orient ellipse vertically or horizontally. And so that's what I'll show you right here. We've got this really nice diagram here of ellipses. And so let's just take some time to go through this. First of all, I give you the definition of ellipse, which you may or may not already be aware of. And let me see if I can just sort of quickly describe for you the way it works. Here's what the definition, here's how you find all the points on an ellipse. I've put a point right here, XY, on that ellipse. Here's what it's saying. If you were to take the distance from one of the foci, oops, hold on one second. If you were to take the distance from one of the foci, right there, that foci, all the way over to that point XY, so this distance right here, right, that distance right there, and you were to add that distance to the distance from the other foci to that point, Now, those distances they're definitely different, but we're not saying, it's not like parabolas where it's the same from the foci to the point and the point to the directrix. It's not what we're saying. What this is saying is you take that distance from one foci to the point, the other foci to a point, and you add them together, right? It says we're sum the two distances, and that sum, right, from here to here plus here to here, that sum will be the same for any point on the ellipse. So whatever that distance comes out to be would be exactly the same number as if I went from this foci to that point and this foci to that point, or from this foci to that point and this foci to that point, right? Those distances will always sum to the exact same number, right? So that's how you get this shape of an ellipse based on those two foci. And in fact, you may have seen someone do this before. What you do is you go ahead and take two of those thumb pins, those pins that you use to stick stuff to a cork board, all right, a couple of pins, thumbtacks, whatever you want to call them. You put thumbtacks down where the foci are. So you just put two thumbtacks down in there. And then what you do is you get a piece of string. You can make the string as long or as short as you want, but the string, right, when you stretch the string out, right, it has to be longer than the distance from foci to foci, all right? If you were to stretch that string taut, it won't work. You've got to have a string that is longer than that distance, all right? So you just tie a string between those two thumbtacks, thumbtack here, you put your piece of string in there, and then you stick your pencil in the string, right? Run your pencil out so that you pull that string taut, and then you just run that thing right around those two foci. The thumbtacks will hold the string at its foci, at the points, and as you pull that string taut with a pencil and trace it out, it'll allow you to get that shape of an ellipse. And the reason is because the length of the string never changes. It's like what I just described. The foci to one point, the point to the other foci has to be the exact same distance. Well, imagine that distance was the length of your string. The length of the string will never change. So you just pull it taut, trace around it with a pencil, and you would get a nice ellipse. In fact, you get a perfect ellipse. All right, so this one is oriented horizontally because my major axis, the longer axis, is horizontal. So let me go ahead and make a couple quick notes for you here. Horizontal. Again, the horizontal one, you can see this right off the formula sheet that I've given you. The horizontal one is going to be x squared over a squared plus y squared over b squared. That's all equal to 1. The other one, the long axis, is oriented vertically. So this would be my vertical ellipse. And again, right off the formula sheet, you can see they switch places. Now the y squared comes first, but be careful. It is no longer over b squared. Now the y squared is over a squared. We'll talk about that in just a second. The x squared is now over the b squared. It is still all equal to 1. And here's what's going on. These a squared and b squared are numbers. They're constants. In fact, actually, they represent the length of the axes. So A will always be the major axis, right? So my ellipse is oriented horizontally because my major axis, the long axis, is oriented horizontally. So because it's horizontal, the x squared comes first and the x squared goes over A because A represents the length of the major axis from one vertex to the other vertex. That's A, okay? Then the y, right, the y is oriented vertically and it's over the b because the b is always the minor axis, the distance from the covertice to the other covertice. It's a constant. It's a number. We will find some number a to represent the length of the major axis, some number b to represent the length of the minor axis. But then it switches. Right down here, the long axis is oriented horizontally. But the long axis is still the bigger number, right? This distance is bigger than this distance, the minor axis. So the reason that it isn't y squared over b squared is because b is the short axis. But the short axis is now horizontal. It's with the x. So the y squared goes over the a because, right, the major axis is now oriented horizontally, so the y goes over the bigger axis, and now the x goes over top of the minor axis. And so essentially, here's a fancy way, or that's a really long way of saying this, a must be bigger than b. And if a and b ever are equal to each other, you have a circle, right? If a is equal to b, then you have a circle. Because in a circle, the major and minor axis are the exact same length. The major and minor axis are the exact same length. That's why you can't have an orientation for a circle. It's the same no matter which way that you look at it. So if a were equal to b, you'd have a circle, but we won't ever get that. A will always be a bigger number than b, and that'll tell you the orientation of the major axis. Some other important things to point out here is this. The vertices are always on the end of the major axis, vertice and vertice. The foci will always be inside the ellipse. If you ever wind up with a foci outside the ellipse, you done goofed. So the vertices will be the points farthest out, foci will be just inside of that, and the foci must be on the major axis. You will never get foci on the major axis, not ever for an ellipse. So the vertices, or the vertex, vertices, whatever, same thing. Vertex, plural, or singular, vertices, plural. Focus, singular, foci, plural, right? Okay, so we've got your vertices at the ends of the major axis, foci just inside of that. The co-vertices will be at the ends of your minor axis. So a co-vertice there and a co-vertice there. Of course, you have your center. I've labeled the minor and the major axes. Same thing down here. Vertex will be at the end of the major. Co-vertex will be at the end of the minor axis. And then finally, one other thing to point out, and I do have it drawn in here, and I will do it again for you. Please notice that inside of this diagram we have these little triangles drawn, both in the horizontal and the vertical orientation, and they're labeled A, B, and C. That's really important because that triangle, right, we're going to use Pythagorean Theorem to help us find something else. Just for example, let's say that in a problem, I give you the coordinate, right, I give you the coordinates of the co-vertices, so you know B, and I give you the coordinate of the focus, so you know C. If you know B and C, you can use the Pythagorean Theorem to find A, which is the distance from the center out to the vertex, right? If you were to take this red line and drop it down, it would be the distance from the center out to the focus. So let me show you how that works. Right down here, I give you, actually, real quick, there is a typo here. That is not manor, it is minor. Minor axis, and here is our Pythagorean Theorem. Do not worry, if you're taking this class with me, I have put this on your formula sheet, except I wrote it like this instead. C is equal to A squared minus B squared. Take the square root. And actually, on your formula sheet, it is also labeled. It says ellipse right above it. So that way you'll know if once you find the value of A and the value of B, let's say you know A and you know B, you'll use this Pythagorean theorem to go ahead and find the value of C. It's labeled right on your formula sheet. You don't have to remember it, but it will be in every problem. You'll be given either A and B, or you'll be given A and C, or you'll be given two of them. You'll need to find the third one, and you'll do it using Pythagorean Theorem. And again, that just comes from those little triangles that we get there, that triangular relationship that shows up inside of these ellipses. All right, guys, really that's all I can say about ellipses. Take a second to study the diagram. I will use all of these terms, vertex, co-vertex, foci, major axis, minor axis. You need to know what those terms mean when we get to solving some of these problems. Again, it'll be just like it was in previous sections. I'll give you some information and ask you to graph it. I may give you a graph and ask you to write the equation, and of course we'll eventually get to ones where I give you this crazy looking equation and you'll need to complete the square to get it into vertex form. So, really excited to go through ellipses with you. Let's jump right into it. I'll meet you guys on the next page.